This problem gives us a current carrying wire and 4 moving loops. It asks us to find the direction of the induced current and the direction of the magnetic force on each of those loops. There's a lot going on in this problem, so let's start by writing down some things we know from the current I. The right-hand rule tells us the magnetic field produced by this current will circulate in this direction, so that above the wire it's directed out of the screen and below the wire is directed into the screen. We also know the magnitude of this magnetic field from Ampere's law is mu naught I over 2 pi r, so that as we move away from the wire, the magnetic field strength decreases. To find the direction of the induced currents, we'll use Lenz's law, which tells us the induced effect always opposes the change in the magnetic flux, where the magnetic flux is the integral of the external magnetic field B over the loop area. Each loop has an area that's perpendicular to its plane, either into or out of the screen. I'm going to take the direction of the area vectors for loops A and C to be out of the screen toward us, parallel to the external magnetic field, and for loops B and D, I'll take the loop areas to be directed into the screen, again parallel to the external magnetic field. That has the convenient effect of making the magnetic flux always positive. Part A asks us for the directions of the induced current in each of these loops. Loop A is moving away from the wire, where the magnetic field is decreasing in strength, so the induced magnetic field will oppose that effect, strengthening the magnetic field inside the loop. From the right-hand rule, we see the induced current, which I'll draw here in purple, must be in this direction, so that the induced magnetic field lines circulate in this sense, coming out toward us inside the loop and going away from us outside the loop. The purple induced current is in the counterclockwise direction. Loop B is again moving away from the current carrying wire, so it's moving into a region of weakening magnetic field, decreasing the magnetic flux. So the induced field will oppose that by being in the same direction as the external field. The right-hand rule shows us that the induced current then must be in this direction, so that the magnetic field lines that it produces circulate in this sense, into the screen inside the loop and out of the screen toward us outside the loop. The induced current in this case is in the clockwise direction. Loop C is moving parallel to the wire, so there's no change in the magnetic field strength, no change in flux, and therefore no induced current. Loop D is moving toward the wire into a region of increasing magnetic field strength, so the magnetic flux will increase, and the induced field will oppose that by being directed opposite the external field. The right-hand rule shows that the induced current then must be in this sense, so that as the magnetic field circulates around it by the right-hand rule, it's coming toward us inside the loop and going away from us outside the loop. The current induced in loop D is therefore in the counterclockwise direction. Part B asks us to find the direction of the magnetic force exerted by the wire's magnetic field on each of these current loops. The magnetic force is the integral of I dl cross B, where I is the induced current. It's constant around each loop, so we can move it out of the integral. dl is a line segment in the direction of the current, and B is the external magnetic field. For loops A, B, and D, where the induced current is not zero, you can make a symmetry argument that the magnitude of the force on the vertical legs is the same. I'll draw them here, with the directions determined by the right-hand rule. dl, the direction of the current, crossed into the external magnetic field B. The important thing is that these pairs of forces cancel for each loop, not contributing to the net magnetic force. That net magnetic force comes entirely from the remaining horizontal legs. Let's look first at loop A. On the horizontal leg closest to the wire, the current is directed to the right, and the magnetic field is directed out of the screen. So the cross product dl cross B gives us a force that's directed down towards the wire. When we move to the top horizontal segment, the magnetic field is weaker there, so the force is weaker, The cross product shows us that the force is directed away from the wire. Adding those two together gives us a net force in the downward direction toward the wire. Notice that the acceleration from this force will oppose the cause of the change in flux, that velocity away from the wire. We can make the same calculation for loop B. On the horizontal leg closest to the wire, the induced current is directed to the right. The magnetic field is into the screen, so the cross product gives us a force towards the wire. On the horizontal leg farthest from the wire, the magnetic field is weaker, so the magnetic force is weaker, and the cross product gives us a force away from the wire. The net force then is towards the wire, giving us an acceleration opposite the velocity in accordance with Lenz's law. For loop C, there's no induced current, so there's no magnetic force. For loop D, the induced current on the horizontal leg closest to the current carrying wire is directed to the left. The magnetic field is into the screen, so the cross product dl cross B gives us a magnetic force away from the wire. On the horizontal leg farthest from the wire, where the magnetic field is weaker, we find a weaker magnetic force directed toward the wire. The net force is then away from the wire, again in accordance with Lenz's law.